Hi, in this short video, I will summarize the main objective, techniques, and outcome of the dissertation, Explainable Hypergraph Neural Networks for the Prediction of Dementia Progression. Dementia affects more than 55 million people worldwide, with 60% in low-middle-income countries. Diagnosing dementia risk early can lead to improved outcomes and lifestyle interventions. However, it is a complex task. There are many risk factors and complex interrelationships to consider. While biomarkers such as brain scans can help to diagnose risk, they are expensive and invasive to collect. Therefore, there is a need to provide clinicians with tools which can help to assess dementia risk without these biomarkers. In this work, we propose to achieve this by modeling low-cost, non-invasive risk factors in a hypergraph, and to use this structure to learn complex interrelationships between features which can indicate risk. On the left, we see a graph, and on the right, a hypergraph. Patients are modeled as nodes and risk factors as edges in both cases. The key distinction is that a graph can only model pairwise relationships between nodes, whereas a hypergraph can capture any number of nodes in an edge relationship. In this simple example, the APOE4 allele relationship is captured as 3 pairwise relationships in the graph, but the hypergraph is able to capture this as a 3-way relationship. This is a powerful advantage as it allows hypergraphs to model higher order interrelationships between groups of individuals and their dementia risk factors. Each node can then be classified as at risk of dementia or not at risk for a supervised learning task. In addition to applying a hypergraph neural network, we also implement a self-explainability module. Explainability is key to fostering trust with clinicians and to understanding how the model makes predictions. By understanding the model's underlying reasoning, we may also be able to discover new risk patterns. This diagram shows 3 typical approaches to explainability. First, it might be completely ignored in the black box model version, where there is little understanding and confidence in how the model makes its decisions. Next, we have post hoc explainability, where we first train the model and then examine outputs. This is an improvement over black box models, but it can also produce misleading results because the explainer module can only examine the outputs of the model, not its actual reasoning process. Finally, we have self-explainability, which we will use in this work. Here, explanations are developed during and with the core model by examining the model's reasoning as it learns. This diagram shows a simplified overview of our model. The core EHNN model is shown in the inside box. It uses multi-head self-attention transformer to learn complex relationships in the data and to make predictions. Outside of this box shows the cache method for explainability. We extract node and edge embeddings on each forward pass of the EHNN model and train a simple MLP to learn node edge importance. The Gumbel max trick is used to sample from this forward pass and to define probabilities for the importance of each node edge relationship. If the score is above a certain threshold, we retain it in our factual subset. If it is below a threshold, we retain it in the counterfactual subset. The idea is that our factual predictions should be close to our EHNN model's predictions if it is correct, and should be the inverse of the counterfactual reasoning performance. After training the model to optimal performance, we can then extract these nodes' edge weights as explanations for the model's prediction. A higher score implies a higher importance and impact over the prediction. Using this technique, we achieved an F1 score of 0.73 and an area under the receiver operating curve of 0.87. The diagram on the left shows this curve for our base model and composite models. The green line indicates a perfect score and the orange line indicates a no skill score. This demonstrates a good skill in classifying both true positive and minimizing false positives. This score also outperforms existing studies trained on similar data using support vector machines and random forest trees. The explainability module raised interesting results. Some were expected according to the literature. For example, we found that CDR scores, a cognitive assessment tool, ranked highly and are a good indicator of dementia risk. Some of the scores, however, were surprising at first. For example, we found that the edge representing no APOE4 alleles scored very highly. Normally, the presence of alleles is associated with strong risk of dementia in connection to Alzheimer's disease. However, on inspection, it seems that the model is likely scoring this highly in relation to other features. The diagram on the right shows a kernel density estimations with histogram of edge scores for different allele counts. We see that the no allele edge scores for each node are on average higher and much more widely distributed than those for the individuals with 1 or 2 alleles. This indicates that the hyperedge score may be a result of the model learning it as an important signal to look for other patterns in the data. In this project, we demonstrated that hypergraph neural networks can outperform existing methods for dementia progression, that they can do so while producing explainable outputs, and that their explainable outputs can be used to assess their reasoning. However, more work is needed. In particular, the data set used contain many biases and missing data. Further, more advanced techniques should be developed to understand the complex interrelationships between edge scores. Thank you.